Thank you. But let's give another round of applause to Scott and Milan. That has to be really hard, like debugging somebody else's code. That's tough to pitch in at the last minute. So I like my title a lot because going back for years in the Persistent Memory Summit here, we used to argue or debate what the media would be, and then we've had some discussion about where to attach. Now I've just heard Jim Papa's kill off DDR-T. Thank you very much. Thank you. And also, we've seen the conference really move to usage, and I think that shows the nice progression in the industry overall. So I like the title about that. I'm a hardware guy. I like things that are governed by the laws of physics. Software is magic to me. So I'm going to focus kind of on a real hardware perspective. So we're going to start off with I love DRAM. Raise your hand if you love DRAM. Oh, I know it's all of you because your companies are buying tons of it and you're using tons of it. We love DRAM, and I appreciate Charles and then also Piotr. We're talking about how persistent memory and DRAM work together in the system. But DRAM does show some signs of age, let's call it that. And a couple things is, if we look at the decades leading up to 2010, we saw an average decline of price year to year of about 37%. Rapid price decline. But what we've seen over the last decade, not including 2018 to 2019, thank you Jim Handy, but we've seen a very much of a flattening out of that price decline. So we're seeing the scaling problems of the technology are coming to the forefront. Perhaps also interesting is the bandwidth, and I took some numbers from J. Thomas Pulowski, who was an architect at Micron up until just recently, and the scaling there has been pretty dramatic. Actually, bandwidth has increased at 31% per year. Now that's incredible. How did it keep up? But how it kept up was adding more channels, adding more DIMMs to those channels, and I'm going to show you that that's running out of steam. You can't keep doing it. So we're going to run into a bandwidth problem on DRAM here eventually. So one of the things we're really looking at here is, can persistent memory do the DRAM job or part of the DRAM job? DRAM is not going away. The future of DRAM is DRAM, okay? Keep that in mind. So let's jump into the media. I like this slide a lot. I took it from IEDM, from a completely different talk, because it tries to summarize the physics between the various types of media that could be used. On the far left, we have flash, which uses a certain physical effect, and then all the way to the right where they've tried to summarize that. Now, I mentioned that we used to debate on the right-hand side here which sort of technology would win. And I personally became very tired of those discussions. And I think we do have a winner in the near term in persistent memory. And I'm going to talk about that in a minute. But there is something new up here. And I don't know if you noticed that. There's ferroelectricity up here. But this is not your grandfather's FRAM. Yeah. This is something a bunch of guys in Germany and Qimonda discovered a few years ago, that if you deposit what's called a high K dielectric in a certain way, it's actually pretty tricky to do, but it demonstrates a ferroelectric effect. I had some involvement with a company a few years ago that's published a paper at IEDM, and we've seen at IEDM the investigation of this go from about 3 papers to last IEDM there were over 30 papers on this effect. So this is something brand new. Now, don't get excited. There will not be this type of ferroelectric chip in the next 5 years. Okay, there's a long way to go. But it does show that physics and material science continues to move forward on memory, and there are new ideas, etc. Very interesting, this was in the plenary talk by Intel. It kind of shocked me about what's called a 1T1C ferroelectric Hafnia bit cell, and that's showing some pretty good results. It's got farther to go on endurance, but it offers tremendous promise in terms of giving a semi-volatile or somewhat persistent memory. So keep your eyes on that. So that's something that's brand new. Now, what do we like or not like about each of these technologies? Well, we all know that NAND flash is just too slow, but we love it because it's cheap. But if we go across here, the ferroelectric one that I just mentioned is very fast, and it could be very cheap, but is way too new. If we jump to MRAM, MRAM has been well studied and commercialized actually for quite a period of time. And the foundries have certainly adopted it, but as an E-flash replacement technology, but it's way too expensive. We really have not seen MRAM getting out as the niche area in terms of being a standalone persistent memory. RRAM honestly has been pretty disappointing. There has not been good advances in RRAM, either as an embedded memory or as a standalone memory. Companies are still trying, but we haven't seen those results. So then we come to phase change, and yes, 3D XPoint is rebranded phase change. Some of you might remember I did a talk with Jim Handy and Tom Coughlin back in 2012, and I did get the audience to chant that 3D XPoint is rebranded phase change. But it does seem to be just the right technology. Don't take my word for it. The rebranded Toshiba, which is now Kioxia, they talked at IEDM last December about how phase change, yeah, they kind of admitted it is the right technology right now for persistent memory. But how do we use it? So I'm going to get into that a little bit later in my talk. Now, who's doing what? I like being an independent consultant because I can talk about things like this. And this gives you a pretty good idea of where things are being done. Certainly over with 3D XPoint, Intel, and now Micron have their own technology. They got divorced here recently, so they'll be going on different paths in the future. SK Hynix has published a paper on phase change. So we expect that at some point they'll introduce it. And I guess I should remove the little dotted line, which means it's a rumored activity around Samsung, because at Supercomputing last November, I saw something where they claimed that in there was a Samsung phase change chip. So we do see the heavyweights in the memory industry here. RRAM, I think, as I mentioned, has been pretty disappointing and is pretty empty in terms of the big guys working on those technologies. What we see with MRAM, though, is it's well adopted in the foundries, but as mentioned, that really goes into that embedded memory technology. And finally, for that new ferroelectric high-K dielectric, Intel, we saw that had a paper there, and there's some rumored activity at Micron and SK Hynix as well. So look for that one in the future. So let's go on to attachment. The guys before me talked about this. They clearly have a love affair with CXL. There is more in the world than CXL, and we'll come to that in a minute, although it looks like a pretty good option. I took this slide from HPE presentation at Supercomputing, and it really talks about if we have this sort of memory, how do we attach it? And their point is, there's tons of options, especially even as you get below kind of this 500 nanosecond breakpoint. There's a lot of options of how to attach things. But most of the things up there are DIMMs. And what are some of the problems with DIMMs? Jim talked about it in one context. If I plug persistent memory in, I have to unplug DRAM, or I have to plug a more expensive DRAM module in. So it didn't always make economic sense, or hasn't always made economic sense, to plug persistent memory into your system on the DIMM slot. And if you look at this diagram, this is one from the JEDEC training class for DDR5. Wow, what are we doing here? That's 16 memory channels coming out of the processor with 16 different DIMMs, and now we're even putting 2 channels for each DIMM. So this is not sustainable, and that's one of the messages I want to get across, and that's why I talked about the bandwidth for DRAM has had a very nice consistent increase year to year, but it's going to at some point start leveling out. So if we think beyond the DIMM and we look at other ways that we can attach memory, and we can attach memory with a lot of bandwidth, that is opening up a side channel which is also coherent. And that could be CXL, or it could be IBM's OpenCAPI, or it could be Gen Z. So that's what we see going forward, is having this side channel is a great place to do that simple job of memory expansion or other things. And I'll talk about that in the future in my talk here. Okay, so if I go back to the presentation I stole from on the HPE guy, I just talked about the direct attach. Direct attach to the processor could be over CXL or OpenCAPI or Gen Z. But there's some other opportunities here as well. And he points out, especially down here, opportunity number 2 is to have that pooled or composable memory. In other words, some place where we pool memory together that those individual nodes can grab memory from that. I thought the Andy Beckelsheim presentation this morning, although his clock rate must be running at about 4 gigahertz or faster, I found it hard to keep up. But he did make a great point that if the network is fast enough, then it doesn't really matter where data resides, and you can move it around. So we could have our data in this pooled location, and it doesn't have to be bound to the node. The other opportunity here is through a switch, and that could be a Gen Z switch or could be another technology switch, and give us that high degree of connectivity. So let's keep those ideas in mind. So if we look at who's doing what, I think the prior presentation made this point, but the one problem with CXL is you can't build anything and hook it up today. And that's going to be another year, or maybe 2 years. We'll see how it all goes. So there are things that exist today. So Arthur's right here. Arthur, go ahead and raise your hand. Arthur from SMART, and there's other SMART representatives here. If you go out to their booth, you can see the very first serial connected memory device, which is OpenCAPI, and that is specifically done for IBM, and SMART builds that for IBM for their new open power systems. Gen Z, SMART also builds, as well as Samsung and SK Hynix have shown, building memory modules or modules that have some level of compute in them that talk over the Gen Z interface, and those interface now to HPE and Dell servers. So those opportunities are there, but we do see that momentum behind CXL, and what I expect, just like I think Jim Pappas, did you announce a new Intel product, CXL? Persistent memory? Okay, that's what I thought I heard, but maybe I was wrong about that. But we should fully expect that. We should fully expect the memory companies to do that, and we should expect them to do it not just with persistent memory, but also with DRAM. Because again, it's DRAM and persistent memory together that make the compute system work. I'm not going to talk about some of the other options here because I've kind of made my case for why you would not use the DIMM, but you would use that side channel instead. Okay, let's finally go on to usage. And again, I'm a hardware guy, business guy. Software doesn't always make sense to me, so I'm going to kind of take a different approach. I'm going to make the point that what is it about persistent memory? What are the applications we should look for that make good business sense? Now, my friend Jim Handy, he did a webinar last week where he said persistent memory without using the persistence is useless. And I wrote that down. I thought that was a little harsh, because I'm not sure it's useless, but I don't think it has a good value proposition. And Jim also, he'll sell you a very nice report that'll tell you that Intel, in pursuing 3D cross-point persistent memory and selling into just a more memory value proposition, is a great way to lose a lot of money quarter after quarter. So that is not a good value proposition, but there is a good value proposition, and we're starting to see it emerge. I think we started to see it here in 2019. Things that are persistent and coherent, things that value persistence and coherence. That takes full advantage. Intel goes to a lot of trouble to engineer persistence into persistent memory. Please use it. So where are places where you'd use it? And this is a slide Arthur presented from, which actually came from VMware in the past. And they talk about, well, let's collapse the tier. Let's collapse the highest tier. of DRAM and NVMe SSDs and put both our hot and warm data into that one tier. So that's a good usage of persistent memory and collapsing that tier, because we value the persistence in that case. And it also can be coherent with the memory subsystem of the processor. So good example. So let's go a little bit further. Intel and OG talked about it this morning. He gave you the Cassandra example. And one thing he didn't tell you was how much does that accelerate the processing, how much advantage that give you. And so what Intel shows is that with Optane persistent memory and using app direct mode versus just using an SSD for Cassandra, they get a 9x performance gain. Okay, so that's pretty fantastic. Now we're starting to see a real benefit in performance. Now finally, the one thing I have not personally seen until last week though, is somebody make an argument, an economic argument, a business argument, why would I use Intel Optane persistent memory? And that was, this is a busy chart, and I'm going to give a shout out. Jing's all the way in the back, so Jing, go ahead and raise your hand back there. Jing's from Formulus Black, and they gave a presentation with Lenovo and with Intel last week where they gave an economic argument. And that argument was for a particular workload. They came down to how much money per transaction does it cost, even considering the added cost of persistent memory in the system. Now that's a business argument. That's an economic argument. And for me personally, that's the first time I've seen that. And that's exciting to me. So we're starting to see these applications. What are some things to look for in the future though? I've talked about one already, and I want to do it in this context. This came from a supercomputing conference last November. All the major supercomputers are heterogeneic. Now, I'm not even quite sure what that word means. It's a great SAT word, but I like pooled, or composable. There's so many words to describe this, but if we pool our resources, and the point is that those supercomputers pool the processors, they pool the storage, everything is pooled. Memory is not pooled. Memory is still bound by nodes. So let's start looking at pooling that memory. And we've seen that. We saw that in the earlier slide, and that's why I pointed it out. So even HPE is looking at what are the benefits of if we pool this memory. Now, how do you connect that? Let's just keep in mind that CXL is great for inside the box. Gen Z is great for outside the box. And Gen Z is an actual fabric that connects things together. So what I see going forward is this could be a Gen Z memory appliance, pooled memory appliance that integrates very well into the data center. So finally, I stole this slide from my friend Stephen Bates. Can we spread a rumor that Stephen Bates is patient zero in Canada for the coronavirus? I think I'd like to do that. Let's just pick on him and see if that's the reason he's not here today. But anyways, he has talked about, and then Scott Shadley talked about this combination of compute plus memory, and also Milan talked about it as well. This is a very interesting application. Now you have those compute resources next to memory. Why don't we use it for computational memory? Should this be a new SNIA initiative or under the SSSI? And Charles Fan from Menverge, his marketing guy, needs to get on this and give us a name. But I think this is an opportunity for SNIA going forward. Okay, so finally to wrap up, 4 things I think. I love DRAM, and it's got some problems. So watch as both the technology scaling and the price scaling gets worse. I think that's an issue on the horizon here. 3D crosspoint and phase change is still the top media for the job, but I think watch this ferroelectric high K. That has some opportunities going forward. The DIMMs, we heard it from Jim earlier, but DIMMs are not a great place to add persistent memory. There's really some drawbacks. So opening up this channel with CXL, I do believe will become the primary attach for persistent memory, and then also some DRAM as well. And that gives you a big bandwidth increase, by the way. And then finally, we have to have applications to drive the business that value both the persistence and the coherence. So pooled memory appliances and computational memory are two things on the horizon that could do that. Okay, and then finally, this is my commercial and how to get in touch with me. Thank you.
Thank you, Dave. I think we have time for 2 questions. Who has a question? He's not that perfect. Who has a question? You must be.
I'll mic drop. No.
Oh,
Go ahead, sir. I think you had a question from the last session, too, so might have to call in some help for this one.
Good presentation, thanks.
Thank you.
Good to get more of an objective view there. So on the, like you're saying, smart modular, and we're seeing some other buses. So OpenCAPI at the moment already is in production. The OMI DIMMs are available. So people that are really excited by CXL could certainly benefit from experimenting with real hardware today. They don't have to wait a year or 2. Any comments on that, on that side of things?
I completely agree with that point. And C6 I didn't mention, but C6 also exists in prototype form in some popular server processors. Yeah, it's a great way to build hardware today and learn from that, whether it's C6 or OpenCAPI or Gen Z. And I think some of the companies are starting to do that, because I think that puts you in a good position. The 3 exciting things about CXL are Intel and Open Standard and Intel, and it's because of the market reach, and give Intel a lot of credit for opening that up. I think Jim alluded to it, that there had been some criticism of Intel not opening up on the DDR-T on the DIMM bus, but to open up with CXL, I think is going to really enable more opportunities for this space. Okay, thank you.